Natalie was right, then I'm probably number 8 in the row of thanking the organizers for putting up this wonderful workshop and also arranging perfect weather for it. So it's nice to sit in the sun today because it's getting quite autumnal back in England this time of the year. I don't have to apologize to anybody having heard this before, because I haven't talked about this before. It's actually quite new. But on the other hand, the reason why it says some comments there is that I will be mainly talking about work that's not actually something that I've done myself, but it's mainly about the content of a recent preprint by Sokola and Taylor, and I will explain a little bit how this comes about and how we got interested in that during my talk. But I should mention that I'm looking at this in collaboration with the Bielefeld group. Michael and Franz are here, and also Dirk Vettel, and there will be a few pictures during my talk that are due to Dirk. Okay, so what is it all about? It goes back to one of the questions that has been around for a long time and still hasn't really found a satisfactory answer, is the question of whether there is a monotile. Is there a single shape that can tile space without gaps or overlaps, but that does not admit any periodic tilings of space? And you know that there is a three-dimensional Einstein due to Schmidt-Conway and Danzer, which essentially does that by creating some kind of a irrational rotation, and in that way it is able to tile space, but due to the irrational rotation there is no periodicity. But in 2 dimensions, the best, in a sense, that was known was a tiling with 2 shapes. For instance, the Penrose tiling, not the only one, but there are others. But there is no known monotile in 2 dimensions in the sense that there's a single shape that would allow only non-periodic tilings. There is one tiling that kind of goes in the right direction in some sense, that is Penrose tiling with a funny name, 1 plus epsilon squared, which I will show in a minute. And the tiling I will mainly talk about is actually quite closely related to this particular tiling. So the story is how we got interested in this is that while I was in Tasmania with Michael working on this book that we hopefully will finish sometime, we got an email from Joshua Sokola, and he sent us a preprint, a joint preprint with a co-author called Joan Taylor, with the title An Aperiodic Hexagonal Tile. Well, just to show the geography, so we were down in Tasmania, which is down here, is Australia, and when we looked at the preprint, we noticed that the address given for Joan Taylor was Burnie, Tasmania, which is, well, I have a blown-up map of Tasmania. So down here is Hobart, where we were working, and Burnie, Tasmania is up there. So it's actually quite a distance, about 250 kilometers or something like that. But what we did then is at one weekend we decided we have a nice trip, so went to the coast here, did some swimming, and then afterwards visited Joan Taylor at home, and so talked to her about this tiling, and so we kind of have the first-hand story of how this tiling came into existence. And it turns out that actually we are probably the only people in this community who have actually ever met her in person, because she had only communicated with Joshua Sokola by mail. And in fact, she is she is someone who has been interested in tiling problems for a long time, but she's not a professional mathematician. She had started to do a mathematics degree with, I guess, what is one of the Australian Open University's equivalents, a distance teaching place in Australia, but then found it too boring, and so gave up. But she had read one of the articles, I think the one in Scientific American, about Penrose tilings at the time. And so she got interested in these tiling problems and has been working on them ever since. And when we visited her, she had a whole room full of nice hand-drawn pictures, and I'll show a few pictures in a moment. Maybe I'll do that first. Come back to that slide later on. So just to give you some impression what she's been working at. So this shows you how she draws some of these pictures. And this is actually a coloring of the triangle lattice, which is related to the tiling I will be talking about. And so this is some hexagonal thing that's also related to some nice colorful pictures. And this is quite nice. So she had a whole collection of these nice pictures in her study. Okay, and yes, and it turned out that actually this preprint, this joint preprint, actually arose from a manuscript that Joan had sent to Sokola, entitled Aperiodicity of a Functional Monotile, and that has since been made available. I'll give the actual references at the end, but this unpublished manuscript, which also isn't going to be published, I guess, is actually available with some nice hand-drawn diagrams, which I will show later on the Bielefeld preprint server. And there is actually a slight definition in the slight difference in the definition of matching rules between these two papers, which I will talk about a bit later. Just to go through these pictures again. Okay, so before I go to explain what this tiling looks like, and the monotile and what it is about, I'll mention a couple of other tilings which it is related to, and the first one is Reventon's tiling. This is made out of square tiles, and the matching rules are such that you have to ensure continuity of these two types of lines. And as you know, this is an aperiodic set of tiles, so you can tile the plane, but only aperiodically. And the way to see that is that these lines form squares of larger and larger size, and so there's no limit to the size of the squares, so there can't be any period that moves, any translation that maps the tiling to itself. And one thing I want to mention here is that you can see that, for instance, these blue tiles, they do form some kind of a periodic substructure here, and the tiling that that I'm going to talk about mostly will also have a kind of a similar feature in that respect. So here is the just showing you these interpenetrating squares of ever-increasing size, and so there's no limit to it. Always in the middle of each square of a certain size, there will be a corner of a square of a bigger size, and since that never stops, it can't be periodic. Okay, the other tiling this is very much related to, and in a sense it is a decoration of this tiling, is the half-hex tiling, which you can find in Greenbaum and Shepard's book. I don't know whether that's the original reference for this, but this is the inflation rule for the half-hex tiling. So we have half a hexagon and inflate it into four, this patch of four of these half hexagons, and you can maybe make it a bit more transparent by kind of making this line a bit shorter, so you actually see it's half a hexagon. And if you add some extra lines, you will see that this will give you some nice structure. So this is just using the inflation rule, you get these kind of hexagons with these lines in the middle, and if I add these red lines, you can see that I get a similar pattern where I have a hierarchical array of triangles. And this is, in a sense, is a very similar structure. So you have triangles of every size. However, well, this is just the triangles, just to show you a bit neater, maybe. However, if you just take this one of these hexagonal tiles, so going back here, so each hexagon has these lines give it a decoration with one line going through and a couple of edges. So if I use just this tile alone, that still admits periodic tilings. As you can easily see, if you put it together, you can get this periodic tiling with kind of three hexagons together, and then just repeat that periodically. And what John Taylor's tiling does actually is find a more complicated decoration that prevents these kind of periodic tilings. So but before I get to that, one more tiling, the one I've mentioned already, Penrose's 1 plus epsilon square tiling. This is a tiling with three tiles, a hexagon-shaped tile, and two small tiles, and the reason for this
name is that you can actually make these tiles very small. In a sense, you can make these blue tiles small in one direction. So that's why he calls it epsilon, because we have still kind of one direction. And these tiles in the corner, which just essentially encode the matching rules in the corners, you can make them as small as you want. You can make them point-like. It's like a matching rule, really. But you can't make both of them as kind of point-like, because if you look at this blue tile, it does have different tilts at these ends. So it does transport information from this edge to this edge, transport information along the edge of the hexagon. Yeah? So you can't transform it into a matching rule, which just is a notch here or something like that, because the end here knows about the end here. So this has 3 tiles, and well, if you wish, in Amamenka tiling, for instance, you could think of as a 2 plus 2 epsilon squared tiling. In that case, you have 2 tiles, but you have 2 matching rules along the edges and matching rules in the corners. But in that case, you can make both of them arbitrarily small, because also the one in the edges, they are just like arrow decorations of the edge, or some notch at the edge. But here, this is fundamentally different, because you actually need to transport the information along that edge. And Andros does give a proof of aperiodicity for this tiling, which is based on giving a hierarchical structure, although that's slightly complicated because the shape of this tiling somewhat changes. Oops, I pressed the button, didn't want to press. Yeah, but I said that already anyway. So the epsilon tile is important in the sense that it does transmit information. So these were kind of a few other tilings that the tiling is related to, and now let me come to the actual monotile. So that's how it looks like as a marked hexagon, and there are 2 versions here. Which this is the version that John Taylor used. This is a version that is due to Joshua, I think. And maybe in some respect you can see some things a bit nicer here, because you see there are 2 tiles here, and they're actually mirror images of each other. But the colors do actually encode something like a chirality, something like a sense of direction, yeah, which is a bit easier to see in this picture, where the colors have been replaced by flags pointing one way or the other. So the mirror symmetry is obvious here. So this is the mirror of this one. You see, the only thing that changes is the flag in these corners here. Whereas here, the mirror symmetry actually does change the colors as well. So you reflect and then change the colors again. So it's slightly more complicated. And the matching rules are the following. So the matching rules that are used in Sokola and Taylor's paper are, first of all the black lines have to be continuous. So tiles have to be adjacent such that these black lines, which are the same kind of decoration that I had before on my tiling that was still periodic, that these black lines continue. And the colored lines, they have to fulfill a funny rule that the colored lines on opposite ends of an edge, so for instance this one and that one, have to be different. Or in terms of the arrow of these flags, the flags have to point in the same direction. Okay? So, yes, these are the 2 matching rules. And when I said that Taylor's original manuscript had slightly different matching rules, there was one additional rule, and that additional rule forbids vertices where 3 equal colors meet, which isn't forbidden in this way. Okay, and you can see some arrangement here, which you can also see the hierarchical structure of the triangles. Okay. So in which sense is this a monotile, first of all? Well, I mean, first of all, there are really 2 tiles, but they are related by reflection, so it's a question whether you count that as 1 or 2. But the matching rules, of course, are such that you cannot actually enforce it by shape. So you can't, because it's the same story as the 1 plus epsilon squared tiling, is that there is an information that goes along that edge. And since there's another tile here, you can't make something that kind of transmits that information from here to here by some kind of shape type modification of the tile. Yeah, and I think I have the next picture. one thing that that you can do, and that's also one thing that was shown in this paper, is that you can make it a single tile if you allow for a disconnected tile, because then you can actually make some bits and pieces that belong to this tile. So these tiles are all the same tiles, just different colors, so you can distinguish which bit belongs to the same tile. So you can make certain bits and pieces here that just enforce the orientation of the next nearest neighbor. Okay. But you can't make a connected tile that enforces that matching rule. Okay, so how can one see that this is aperiodic? And there's actually two proofs in the preprint, and the second of which is the one that Taylor originally used, but this is the first one, which maybe is very much similar to the Reventon tiling idea, and uses the hierarchical structure of these triangles. And how does that work? First of all, you can see that in any tiling you must have these small rings forming, because if you start with one tile and you put a second one adjacent to it, either you put it in this way and then immediately the only thing that fits here will complete that small circle, okay, that small triangle. Or if you put one of the long edges here, then you have to put another long one here, and then you see that you are forced to complete a small circle there. So you always have to have small circles, you can't avoid that. Once you have one small circle, one of these small triangles or circles, you'll actually have to have one on the opposite side, which is due to the way that this tile has to be positioned due to the different different color matching groups here. So there's no other way to do that. So if there's one here, then there has to be one here as well. And if you iterate that argument, you'll find that there is kind of a periodic structure hidden in this tiling, because all these circles or little triangles are forced, and the colors, these colors are forced. Note this is only part of the colors. There were, on the tile there are actually two colors that go through, and there's one line of color that changes color in the middle. There was a red-blue line. I don't know whether that's, shall I go back maybe just to show the tiles? Yeah? You have two lines of color, the blue and the red one that go through diagonally, and then this line that goes through the two little black curves here, that changes color as it goes through. Okay? And then you have the other black line there. So only part of the decoration is fixed, but part of the decoration is fixed and fixed in a periodic way. Yeah? So you have this kind of underlying periodic structure in the tiling. And that's a bit similar, I guess, to what you have in Robinson's tiling, where you have this blue color tile in my previous transparency that is forced to be at every fourth position, essentially. Okay, so you get that. And now you have to fill kind of these gaps. And how do you do that? So if you start filling one of these gaps, so there's a gap here, well, that was the gap, so I just filled in one thing. The only thing you can do is you have these notches, and they have to fit the other black lines. So the only way to do it is to have an arrangement like this. And once you put that in, then that forces all these other colors around. And what you see then is that you have a big hexagon here, the dotted hexagon, and it looks the same as before. You have these kind of markings, and actually what you see is that you get the same type of matching rule enforced at this scale. So this was the original hexagon, like this, but now the big hexagon has to fulfill the same type of matching rules, that these things have to match across the corner, and also that color constraint does actually transmit along these lines. And then maybe a picture to show that more clearly. That is due to the fact that if you have a color here, say you have blue up here, that's still not fixed, it could be blue or red. So if you have blue in this upper part, so blue, if this part is blue, then because of the matching rule, this part has to be red, and then this part is blue again. So you the matching rules automatically transport along the edges to the next bigger hexagon. Okay. And what happens then is you're kind of forced to do the same type of periodic substructure, but now with a bigger hexagon. Okay? And so this is trying to show this how this works. So you see the gray hexagons are the original ones that I had with forming these little rings. So they are the gray background here. And then the next one you fill is one of the green ones. Once you filled one, you get these corners here. You are forced to complete triangles with the other green ones here. And so you get another periodic pattern of green hexagons. And that leaves new holes. And then you have to look at what fits into the new holes. And into new holes, you get another set of these corners. And they force you to make larger triangles which are closed with another periodic substructure. And so you get lots of these interpenetrating periodic substructures forming larger and larger triangles. So the argument is very similar, I think, to the one for the Robinson tiling. And the matching rules work in a way that this fits. So you can see that the kind of this color rule of changing colors kind of automatically transmits correctly. So it gives you it fits together correctly. Well, you certainly have a choice to start with, and then there's always, at some stage, there's still some decoration was still not fixed on the previous level. But once you have put the next level, it does fix part of the decoration. And so I think, well, the way they argue is that to show that you actually can get an infinite tiling, what you do is you keep one hexagon free. You never fill that. And you go on filling all the others, and then kind of each level you go and you fill a larger and larger portion of space, because the next free one will be further and further away. And then you have, in the end, you have a freedom of fixing that final triangle, and there you're the final hexagon, there you're completely free to fix it. So you could either have the long line going this way, or in any of the 60-degree directions, or 6 directions, and then you also have to fix the color, the changing color line, and that will fix all the other changing color lines. So in a sense, I guess the next hierarchy determines part of the coloring of the previous hierarchy. And so you end up with this. If you do it in this way, that you keep kind of your central tile free for all the time, you end up with this prescription with one particular tiling. Well, not with one particular tiling, but with one tiling apart from changing maybe some of the colors there. Yeah. But that's what they call, I think, the CHT tile, central hexagon tile, something like that. But this is actually not the only tiling type that is compatible with the matching rules, because there is one other possibility, which that's why I mentioned that difference between the two definitions of matching rules. If you allow for, well, first of all, if you look at this tiling, you will find that there is never a vertex where 3 equal colors meet. Okay? You always have 2 red and 1 blue, or 2 blue and 1 red meeting at each vertex. But if you allow for this type of 3 equal color vertex, then actually what happens is that one vertex determines the whole tiling. There's only one way to continue. You can only continue it in one way, but you can continue it consistently. So it's a bit like in the Penrose tiling. If you start with a decagon with the wrong arrow decorations, with a defect type thing, you can have the situation that you can extend it, but only in one particular way. It's a bit like that. So having this relaxed matching rules allows for a different tiling, which is not equivalent, not locally equivalent to the other tiling. It's also not repetitive in the sense that that vertex can only appear once. There's only one such vertex. Okay, so that's kind of the argument from that preprint. Okay, so next I'll try to explain, hopefully I get it reasonably correct, the approach that Taylor originally used, which is based on the substitution argument. So the figures, I did choose to use the hand-drawn figures because I think they're actually quite good to try to explain that. And the way this works is she starts actually from half-hex tiles, which are marked in a certain way. So there are 14 actually of these tiles, and they have these lines which already look a bit like the decoration of the hexagons, so not surprising. And in addition, there are letters along the edges, and the letters come in two types. There's either things where it's A, B, C, D, E, F, G, I guess. And there are also the ones with a bar on top. There's a G bar, for instance, here. And the matching here is such that you are only allowed to have adjacent letters which are exactly the same. So G bar only fits to G bar, not to G. And G bar, or A and A bar, they are kind of a chirality again. So it's a different sense of direction. So if you reflect, then an A becomes an A bar. Yeah. Okay, so there are all these tiles, and yes, okay, and if you look at all these many tiles, there is essentially you can put them together to form hexagons. Most of them you can actually put together to form hexagons only in a single way. So there is an AL tile and an AR tile, and actually AL and AR are the only ones that fit together to make these inner letters work. There are only two exceptions, in that are the C tiles. They fit to the, I think, to the E tiles. The C tiles fit to the E tiles. I think these are the only exceptions. Otherwise, you can only put them together in one way. Okay. So here are just all the hexagons you can make. So there are 7 hexagons, and they're mirror images, and there are a few more here. So that in total there are 9, and they're mirror images. But what happens with these two? These are the two that you make by putting a C and an E, two different half hexagons together. They actually don't occur in any tiling because you can't complete them to a tiling. That's what these pictures down here show. If you start with one of these, this is what she calls an H tile here. This one, then the labels here force you to put these type of tilings here, and then the decoration doesn't fit. So these actually don't occur. So really, you only have 7 hexagons and the mirror images in any tiling of space. And each of them is composed of 2 half hexagons in a unique way. So that's just a way of encoding that. The reason using half hexagons is that the inflation becomes somewhat. So that's you get to. And this is essentially the inflation. And how did she get the inflation? What she did is she started with one particular tile, which is the C tile of these half hexagons. So all these tiles in the middle are the C tile, and looked at all possible neighborhoods that you can make. And this is actually listing all the possible neighborhoods. Well, there are 1, 2, 3, 4, 5, 6, 7 here and 7 here, and then there are 2 at the edges. And the reason there are 2 at the edges are that these are, again, cases that cannot occur in any tiling. So they're actually not, well, you can put the 4 tiles together, but you can't continue. So they are not of interest. So you have these cases. And if you look at them, what you get is actually, these are looking like scaled. If you look at the labels, then the scaled copy here is of the type, in this case, is a type A, and this is a type B, and so on. So you get the original tiles back at a larger scale with the same type of matching with the same lettering. If you keep for the lettering of the big tiles, you only keep the central letter here and discard the two letters that were in these corners. So that's kind of where she got the inflation rule from. Yes, it is shown again. So these are the original half hexagons and the way how they're dissected. And the reason that works, that this is enough, is I can show you here. Oh, this is. Let's go back. Okay. Well, this is just the same. I think this is just the same again. So going the wrong direction here. Okay. The next, but she still needs to say something about the tiling to make sure that you can actually go in both directions. So that's the next argument to be made. And that works a bit similar to the previous argument, although it's kind of slightly different, I guess. And the first thing is that you have to realize that certain of these, where are the hexagons? Certain of these hexagons have to appear in any tiling. And there has to be at least one of A, B, or G type. A, B, or G type, I think. That's the first thing she uses. And you can see that by, if you start with any of the other tiles, like D, F, or D or F, here, then you are forced by the matching rules to have one of the other tiles there. And then, once you know that there is an A, a B, or a G tile, you start with all these possibilities, and you find out that the A, B, and G tile, they always have to occur together in such a configuration. There's no other way to have them in the tiling than the three glued together. And that's why she calls this a glugon. So this is three hexagons glued together, and they're always A, B, and G tile. So this is these pictures just show the argument. If you start with an A tile, you cannot complete it any differently from having a G and a B and a G here. Or if you start from a B tile, you're forced to have the A and the G here. And if you start from a G tile, you're forced to have the A and the B here. So they always occur in that configuration. And once they occur in that configuration, then actually the matching rules, these letters here, force you to have C tiles in all these corners. So you have a C tile here, a C tile here, and a C tile here. And these C tiles now make this kind of periodic substructure, which is similar to the periodic substructure that I had before. So this is what is shown here. So you have these glue guns here, and then you have to fill it up with C tiles. And once you have the C tiles here, you're forced to have another of these glue gun configurations here with C tiles here, and you get this structure, which is very much the same as the structure I had before. That leaves you these big holes, and in these big holes you can't have the ABG type arrangement because it doesn't fit anywhere to the wall, and that forces actually the tile in the middle of this configuration to be another C tile. So you have C tiles on a triangular sublattice of this structure. Okay, so this structure, what she's done now essentially has shown that you can, rather than using 14 half hexagons or 7 hexagons, you can also use 3 tiles to tile the structure. One is this three hexagon configuration, and then this big thing which fills these holes. There's only one type of configuration here, which can go in here as well. And then there are the single C tiles which make up this triangular background. Okay. Okay, and this is just a picture of using the inflation rule. So you can actually, yes, you can. Well, it's just showing that the inflation rule works with all these letters and matching conditions. Okay, so this is the second stage of reduction, where now you have these 3 tiles. You want to go to a single tile, and the way that's done is that these 3 tiles only occur in these certain configurations, and the single tile is actually then this big tile, which you can see as a dotted line here. So she uses this big cluster plus the surrounding configuration to make up one of these big tiles, and then the colored lines, they are derived from looking at the matching labels at the outside of these clusters. So you can see that this big cluster, it has 2 colored lines going through, which are same color, and then there's one line that changes color here. And you have these wiggly lines here, which are the matching lines I had before. Okay, yes, this is just another picture, picture of the same thing. So you can see that how these fit together. Okay, so what is shown really there is, well, there was the inflation rule, which was kind of the second picture already, which shows you that if you iterate the inflation rule, you get an infinite tiling, and that tiling fulfills the matching rules because the inflation rules was made in that way. On the other hand, if you know that you have this structure, this structure with all these C tiles here, then you can look at, since she looked at the matching rule was based on taking all possible configurations around C tiles. You know that the configurations around the C tiles are on the list, and so you can do the deflation procedure. And since since you are living here on this, the C tiles form this triangular sublattice. So if you take the surrounding of these C tiles, you actually get the whole structure and can deflate it with that deflation rule, and that by construction also fulfills the matching rule. So I think she has shown, if I understand it correctly, she has shown both directions, which means that that tiling is aperiodic, the matching rules, and that you get a single Li class from this particular rule. And so, of course, that is kind of slightly different from the other in the sense that here you will also have the additional rule that never three equal colors meet. Otherwise, you would get more than one alike. So that was used, actually. I should have mentioned that. That was used, I think that was used in ruling out some of these, in the analysis of what configurations are allowed. Forward again. Yes. Just a couple of pictures here. This is pictures made by Dirk for this tiling, just to give you a view how it looks like. So this is the pseudo-inflation for the hexagons, and you can see that the central hexagon is always of the same type. This is the C thing, which is, well, it is the same as in the previous inflation rule. You had always the C half hexagon sitting there, and well, yes, of course, now you have to have the C always in the middle, and you can see that if you iterate that inflation rule, that is the reason why you get these C hexagons appearing all over the place in this submap. This is a picture how it looks like, and you can see this C hexagons appearing all over the place. Okay, so the final bit is the question: how is that related to Penrose tiling? And again, these are pictures by Dirk Fettler, who has just looked at it just last week, I think. He has been playing with this and trying to figure out how the relation is. And if we understand it correctly, it is locally derivable in one direction, in the sense that from the Penrose tiling you can derive this tiling in this way, and I think the next picture shows it maybe a bit clearer. So that that hexagon is replaced by this hexagon, and then also that little corner tile is replaced by hexagon. And if you apply that rule, you can get from the Penrose 1 plus epsilon squared tiling to the Taylor tiling. And the other way around, it is a 3-to-1 map, in the sense that you can choose one of three sublattices of hexagons, and if you just take, so that these three hexagons here are forming, well, I mean, there are hexagons in between which are left out, but these three hexagons here, if you decorate them in this way, they will give you a derivation to the Penrose 1 plus epsilon squared tiling. But there is a choice here because you can start from one of the other sublattices, so there are three choices for the map in that direction. So apparently it is then not mutually locally derivable because it's kind of derivable one way, but in the other way you have a choice. The rule was from Penrose you get this hexagon type, but not that apparently. The half hexagons, yes, they are just half they're really just half the hexagon. Just cutting. So you have to cut them. Yes, but the markings fix which I think they do. Yeah, they fix which direction the. Not sure. I don't know. Okay. Yes. Well, this is the final thing. Just to mention that. One thing, there's some nice pictures, and there's also another preprint now out forcing non-periodicity with a single tile by Suitor and Taylor, where they make some kind of three-dimensional versions of thickened tiles, and then of course you can actually encode that matching rule by shape, because you can make things in 3 dimensions which you can't do in 2 dimensions. Yeah. You can transport along the edge by going around in the 3rd dimension, so you can do that. Yes, but it's not flat, of course. But then it doesn't. Then of course it's periodic in the other direction. Yeah. So it does kind of encode the planar matching rule, but by a 3-dimensional shape. And then of course you only need one as well, because the mirror tile is actually the same, because you can turn it around in 3 dimensions. So that's okay. So these are the references. There's essentially these 3 papers. This is the original manuscript by John Taylor, and then these are the 2 papers, which I think are currently being refereed, I guess. This one is being submitted to Journal of Combinatorial Theory, and this one to Mathematical Intelligence. So then, well, we'll see whether that will come out soon. One thing, maybe a few final remarks. One thing is maybe question how to call these tilings, because of the slight difference between the 2 definitions. It's really kind of 2 different things in a way. Yeah? We have the stronger matching rule that enforces, which seems to be perfect matching rule because it enforces a single Li class, and on the other hand we have the somewhat relaxed matching rule which allows for the kind of different versions. So I was wondering whether it might be sensible to call them different names, having kind of Taylor tiling for one and Sokola Taylor tiling for the other, something like that. Well, I don't know. I'll have to see. But certainly it's an interesting progress, I guess. But it is very similar to Penrose's 1 plus epsilon squared tiling. So the question of whether there is a single tile, I guess, remains open for the time being. Anything else I should add? The disconnected one, I had one earlier on here. Yes, they are the disconnected. So I mean, these bits essentially transport the information to the next one because they are kind of I think they're rectangles, so they only fit together one way but not the other. That's the way that it. So you can do that. Okay, thank you. I have forgotten something. Jeb prepared some puzzle, yeah, and Michael kindly brought it along. So if you have some. If you want to, you can in the break time or whatever have a little play with these monotiles and try to arrange them. So I'll leave that.